My name is Paul Hayes and I'm one of the Pro-Vice Chancellors here at the university. And as I say, it gives me great pleasure to welcome you here to this public lecture this evening. So our speaker, Stefano Liberati, is an astrophysicist and a professor at CISA, the International School for Advanced Studies in Trieste, Italy, in the astroparticle physics group. Stefano comes from a really great pedigree of astrophysicists. He was the final student of Dennis Sciama, the same Dennis Sciama after whom the building that houses our Institute of Cosmology and Gravitation is named just across the road there. Just to show you how great that hereditary, that pedigree is, it's interesting to see that Dennis's first student was George Ellis, his second student was Stephen Hawking, so some great names have come out of that. So Stefano received his PhD in 2000. Dennis Sciama, I've just heard, died in 1999, just after he had seen the first draft of Stefano's thesis. That is, of course, pure correlation. Yes. So after his PhD, Stefano went and studied in the States at the University of Maryland, and then he returned to CISA as a tenure-track researcher, and in 2010 he was promoted to associate professor and full professor since 2015. He is the astroparticle PhD coordinator from between 2011 to 2016, and he's presently a member of the steering committee of the International Society of General Relativity and Gravitation and of its Italian counterpart, SIGGRAPH. His research fields are within the theory of gravitation, ranging from the phenomenology of quantum gravity to analog black hole systems and to quantum effects of gravitational fields. He's the author of about 150 international publications and some popular articles, including in Scientific American. Apart from that, he is a fan of science fiction, but only real science fiction, i.e. that is built on science rather than fantasy. And it's about science of science fiction that Stefano is going to talk to us this evening. Stefano. Thank you.
Okay, can you hear me? Fine, okay. First of all, thank you for coming so numerous. I mean, I'm really impressed that this talk can attract so many people. What I'm going to tell you about tonight could be just the ranking of a scientist, you know, not liking some of the extreme science fiction that sometimes is presented. But I would like also to, my tentative tonight will be to show you that some of the science related to science fiction can be as science fiction, as intriguing, as mind-boggling as the science fiction that we are used to. I mean, there are really things that we are discovering every day about the nature of space-time, which are really amazing, and in a sense, reality is sometimes even more exciting than science fiction. So let me start with a brief addendum. Why I'm giving this talk? You know, for a physicist, watching science fiction movies, for example, is always a kind of pleasure mixed with pain. Not because you have the things, oh no, he's gonna do it. Now there is a monster coming out from a singularity, and you say, no, that's not gonna happen. And then sometimes it happens, sometimes instead it doesn't, and you are very relieved. But there are movies really that drive you nuts because they pretend to be science fiction, but they don't respect the rules of physics. So I mean, you can appreciate them as fantasy movies. They are perfectly fine. I actually like fantasy movies, and fantasy, there is no rule to be respected regarding physics. That's fine. Fantasy, for me, is perfectly recreational, perfectly acceptable recreational activity. But when you want to be a science fiction, you have to respect the rules of physics. That's the basic rule. So sometimes the physicists react very badly to this and need, at least I need very often this kind of, so then or you just stop there, or you basically say, okay, if I am invited to, I'll try to give what is the physicist take on some of the things that appear often in science fiction movies. And of course, I'm working in gravitation theory, so today I'm mainly going to talk to you about aspects related to sci-fi from gravitation theory, and there is a lot to say, as you can imagine, because the gravitation theory is dealing with the very fabric of space-time. Of course, in order to discuss the relation with sci-fi, I want to be sure that everybody is on the same foot regarding what is gravity nowadays. You see, our daily experience of space-time is something that is very regular and straightforward. It's what we learn in school, Euclidean geometry. There is time is flowing, and there is a system of 3 coordinates for space. Of course, we all know that we live in 4 coordinates because when we give a meeting to someone, we say, I meet you at the Denishama building at 4 o'clock. You don't say, I meet you at the Denishama building, and then say, when? Or you say, at 4 o'clock, where? So you need to give all the 4 coordinates in order to pinpoint a location in space and time. But of course, this is a non-dynamical space-time, and we are used to seeing gravity as something that attracts body toward the ground. But of course, this has completely changed with Einstein. You know, the big realization of Einstein is that what we call the force of gravity is nothing more than the fact that space-time, what we call space-time, is a dynamical entity that can be bent, curved, can change shape, can react to excitation and so on, can vibrate. So this dynamical aspect of space-time is what makes possible all the things that we are going to discuss tonight. Okay? And the Einstein equation, I put them just to scare you, but they're basically saying the geometry of space-time is reacting to the content of energy and matter in the space-time. Nothing more than that. Of course, it may look like general relativity is something like very scary, and that the Einsteinian theory is something that is very remote from our daily experience. There is nothing more false than that. You have devices that are using both special relativity and general relativity in your pockets right now, most probably. You know that your mobile phone, when you use a GPS location, you're actually using a system of satellites in orbit. And in order for this localization to be accurate, the clocks of the satellites have to be synchronized with your clock. Now, the point is that Einstein taught us, and this is special relativity, that moving clocks are ticking slower than clocks that are standing still. While general relativity is telling you that if you are up on a mountain or you are deep in a valley, the one deep in the valley, the clock ticks slower than the one on the top of the mountain. Time, again, is dynamical, is the first concept we learn. So time and space can be bent, can be dynamic, and can feel the gravitational field of the Earth, right? And can be influenced by the gravitational field of massive bodies. So if we look at the satellite is moving with respect to us. So its clock, by special relativity, is going slightly slower than our clock. But at the same time, it's higher in the gravitational field of the Earth, so its clock is going slightly faster. Who wins? General relativity. Gravity always wins. So at the end, what is happening is that they would make a mistake of several nanoseconds if not taking into account this. And your GPS localization will be completely useless in a matter of minutes. So you're using general relativity and special relativity in your everyday life. It's not true that these are metaphysical concepts. When it was a bit more than 100 years ago proposed general relativity, people thought that it was almost metaphysics and that could have no application in the life. GPS saved the life of many sailors. Think just at the problem of longitude and the development of the first chronograph, just to solve that problem. and now is solved definitely with the GPS. So general relativity is an everyday experience by now. But still, it's mind-boggling. I mean, if you take seriously the same theory that allows you to find a building in your town without any problem, the same theory predicts among the most extreme phenomena in our universe. So you cannot take just the GPS. You have to take also the extreme phenomena with you. And I will start talking with the less extreme, black holes. Tonight, this is going to be the most conservative part of the talk. So first of all, black holes were rejected by Einstein. Einstein didn't like it at all. The first black hole solution was found a few months after the publication of general relativity, and was basically published in 1916. The author, Karl Schwarzschild, died, unfortunately, in First World War. Another brilliant mind that was wiped out by war. And Einstein, for a long time, also Eddington, for a long time, rejected the idea of black hole because they were so extreme, so strange, that he couldn't accept that it could be a real physical solution of his theory. Now, black holes are a sci-fi classics, right? This is just an example of 3 movies that are very much into black hole physics, let's call it this way. But what we really know about black holes? Okay, black holes are the very extreme objects. So what is happening is that when a gravitational collapse is not stopped by some matter physics, a star cannot find a new equilibrium, and basically is becoming so dense that even light is trapped. And so the black hole is black in the sense that light is trapped. It's interesting to note that the idea of a black hole is actually much older than Einstein. It's dating back to the late 18th century, basically, and it was proposed by John Mitchell. John Mitchell was a British natural philosopher who basically had this very simple idea. You know that in order to escape the Earth, there is a limit speed that you have to reach, which is basically goes like the square root of the mass and the inverse of the radius of the planet. Now imagine that you take the mass of the sun and you make it more and more compact. So what is going to happen? It's going to happen that at some point the limit velocity to escape from this star will be faster than the speed of light, but nothing can travel faster than light. John Mitchell already knew that. And basically what is going to happen, that light is not able to escape and the star will become dark, a dark star. Of course, the idea behind this was that any object, if I throw it up and then if slow down and then fall back, right? But think about it. It means that light, in order for this picture to work, should reach 0 velocity and then come back like a rocket. But light travels always at the speed of light. How can it come back? So, for example, this is something that, this is the reason, partially, why this idea was abandoned. Because Laplace later exposed the idea and then thought about light as a wave, and it basically it looked like the wave had to slow down, but light should travel at the speed of light. What is going to happen? So, sometimes, in order to really understand things, one has to step back. And I will tell you an analogy that will come back handy later. The analogy is the following. Imagine that there is a waterfall. So water is flowing in this direction, and at some point it becomes faster than the speed of sound in the water. Now, generally what it does, a physics professor takes his most voluntary graduate students, and the graduate students is supposed to emit sound while it's falling through this kind of stream, right? Now, the sound is dragged by the stream, right? So what is happening is that the waves of the sound are dragged in the direction of the stream. If the stream becomes supersonic, all the waves, so these are different, it's the same wave at different distance of time. 1, 2, 3, 4, 5. So what is happening is that all the waves are falling into the stream, into the waterfall, and are not reaching the professor, which is safely eating the sandwich here.
So what the professor will hear? Will hear the graduate student say, oh! Why? Because the waves that are trying to escape are stretched and they have to fight against the stream. So they are stretched and they basically become more and more long wavelength as they escape the stream. And so you hear, oh, and then nothing. This is sometimes called a silent hole or an acoustic hole. Initially it was called dumb-hole, but I was told that this is something that is not the right, they had to change the title of the paper. So, and you know, these are things that appear in nature. Now, it looks like this has nothing to do with a black hole, but of course it has. So now, what is happening with a black hole? With a black hole is exactly the same story. Replace the sound waves with light waves, with light, right? And replace the flow with the curvature of space-time due to the fact that there is this very dense mass that is curving the space-time very dramatically. What is happening is that these are the light constants. This is time, this is space, so this is the line, if c is equal to 1, this is the line that is drawn by light, and this is adding another dimension, so it is called the light cone. And you see they are bent toward the interior of the black hole, and this is why basically light cannot escape. It doesn't travel, you know, slower. It just is bent, it's dragged inside by the flow of space-time. So this is the light. Light will travel in this direction, and particle with a mass will travel along this. And you see, as they go closer to the event horizon, the limit of the black hole, they are basically dragged inside. They cannot do anything else and go toward the interior of the black hole. The black hole are very dense objects. Imagine that if I would take the sun and make it a black hole, it would have like a radius of about 3 kilometers. Can you believe it? All the mass of the sun in 3 kilometers. That would be a black hole 1 solar mass. Now, I hope that this is clarifying a little bit what is a black hole. Now, you see, the thing is that the gravity of a black hole is so strong that it can do amazing things to light. So, imagine now we have a black hole, and we are trying to answer the question how you can see a black hole if it's black. Of course, normally there is matter around the black hole. Imagine you're a drain hole in your tap, you know, in the basin, in the kitchen. There is stuff rotating around, going inside the hole, right? Now, normally there is matter outside, and this matter is basically flattening as a disk around the black hole. What you could see? You see, imagine we are looking from this direction. So, from this direction, sorry. Then you would see, amazingly, not just the side of the disk around the black hole, which is on your side, but gravity is so strong that the light rays that normally would go this direction are bent and are coming toward you as well. So you don't see just the hole. You see also, it's like the disk around it is bent over it, and you can see also the back of the disk. Isn't it amazing? Light is completely bent by it. And this is a reproduction of what you would see on a university computer. And this is, of course, an Hollywood computer. But I just want to make a comment that this Hollywood computer is not as precise as it could be. They took away, just to not confuse people, 2 effects. This side should be brighter than this side. Anybody can guess why? Because there is rotation. So rotation makes in such a way that there is a side of the hole, the accretion disk, that is rotating toward you. Another one is rotating away from you. And this makes a difference in the light. But they took it away from the interstellar black hole because it was too confusing. Okay. So, bad news, black holes are ubiquitous. You know, initially, people thought, okay, these are extreme things, they are basically, probably they are, you know, a theoretical possibility, but if the collapse is not isotropic, things may avoid to form a black hole. No way. Now, by now we know that there are many sizes of black hole around the universe, and there is one lurking at the center of our galaxy of 4.5 million solar masses. So 4.5 million solar masses, what it means? It means that roughly, if you calculate the radius, you have to multiply by 3 kilometers. One solar mass will be 3 kilometers, given that the radius scales like the mass. So you do 3 times 4.5 millions, and then you have your mass is basically around 13 million kilometers. Isn't huge? It's tiny. We have a kind of discrete black hole, and it's quite an embarrassment for the Milky Way. We have a supermassive black hole, but really in the final part, supermassive, but not so much. Let's put it this way. This is just to give you scales. So, okay, this is one that we've seen is 5 billion solar masses. Okay, it's basically 5% of the mass of the host galaxy. But this is not. They are nothing. So here is really a gigantic one. 40 billion solar masses. Make your math. How large it would be? Well, it is showing you. It's taking basically, it would be as big as a big chunk of our solar system. You have to take 40 billions, multiply by 3 kilometers, and that is not taking into account rotation and so on, and you get something which is 120 billion kilometers. Can you imagine? I mean, if this is not extreme, I don't know what it is. We are going to get to more extreme things. You know, there is one point. If I would have given this talk not too long ago, less than, let's say, a year, a bit more than a year ago, I would have told you that we have all this indirect evidence that there are phenomena there and objects around which there are stars moving that must be so compact that only black hole can explain this. But now, this is not uncertain anymore, because we saw in 2016, actually in September 2015, but the publication is 2016, the merging of 2 stellar black holes, right? These 2 black holes were 26 and 39 solar masses. They merged to form a 62 solar masses black hole. Now, take 26, let's do our math. 26 plus 39 is not 62, it's 65. Where 3 solar masses ended up? They ended up in gravitational waves, ripples in space-time, that was so violently shaken by this merging of this massive and ultra-dense object to create ripples that traveled through millions of years and arrived on Earth and were detected by us. I just want to stress this point. So this was the first direct evidence that black holes do exist. It was not just the discovery of gravitational waves. Now we know that black holes, as the one in GR, to a very good accuracy, are there. Okay? But it's also amazing the energy that was released. You see, if you think 3 solar masses, but they were released in microseconds. So what is happening is that at some point at the merging, the power emitted by this event was 200 solar masses per second. Think about it. An event emitting 200 solar masses in a second. It was, for a moment, the most bright object, the most powerful object in the universe. And these are, again, the numbers that GR, the general relativity, make us confronted to. And later on, we have recently, well, this is really fresh news, we have even seen the merging of 2 neutron stars, which are the next 2 most dense state of astrophysical object. The neutron stars are the most dense star at the moment that we can conceive or we have observed in astrophysics. And it's nice because in the case of neutron star, given that it takes more time to merge, I can even give you the sound of the merging. This was the first marriage of 2 neutron stars. We don't know if they formed a black hole or another neutron star. This is something that is under investigation. I just want to make one final comment. You know what we had to do to observe gravitational waves? We had to build
machine able to discriminate the displacement of 1,000, that means 1 divided 1,000 of the size of a proton. Think about it for a moment. This was really an achievement. And I want to stress this because, you see, sometimes I think as humanity we shouldn't be proud of what we do, right? But I think that of this we can be proud because only 30 years ago when they start thinking about this experiment, people will say, no way, you're not going to see anything. You're not going to see anything because you have to have this kind of resolution, displacements which are smaller than the size of a proton. And nonetheless, we made it. We made it, and I think we all made it. The taxpayer that paid it prominently was the first person that can say we made it. So maybe in 1,000 years, nobody will remember our small wars and our errors, but maybe they will remember us for this, for what we were able to achieve working together. I think that this is a very important message from science. So going on black holes, I just want to touch on another point, that black holes are also the place where the marriage between gravity and quantum mechanics comes into place. So where basically you can use quantum mechanics, which is the other pillar, let's say, of 20th century physics, to predict what the black holes are not really black. And this is quite an amazing thing, because it was realized in the late 60s and early 70s that a black hole follows some theorems of general relativity, some laws, so-called laws of black hole mechanics, which are one-to-one in relation with laws of thermodynamics. But people say, well, how is it possible? They cannot radiate. They are black. They are completely black. So how an object can behave thermodynamically if it doesn't have a temperature? Stephen Hawking, putting quantum mechanics, putting quantum mechanics in the description of matter moving on a black hole, discovered that virtual pairs, the vacuum becomes a kind of effervescent things. Virtual pairs are always created and destroyed. When you are close to the horizon, one can be taken by the horizon and the other one escapes to infinity and they become real at the expenses of the energy of the black hole, which reduces size. And the temperature of the black hole goes like the inverse of the math. The maths. The smaller the black hole, the hotter. I'm giving you all these points to lead you then to some relation with science fiction. I hope you allow me this. Just want to make one last comment. Of course, this temperature is very difficult to see, because if you take a black hole and you ask when it has the same temperature of the cosmic microwave background, the radiation that fills the universe, which is at 2.7 Kelvin, well, you get that you need a 60 micron black hole, which is really tiny one, which is very difficult to see. Imagine in astrophysics, you are looking at billions of away, and you say, look at 60 micron black hole. This is even worse than the gravitational waves task. So people is ingenious. And the analogy that I gave you before, and this is just an interesting fact, can command it. So how it commands it? I gave you the analogy between an acoustic black hole and a real black hole. Well, the fact is that the analogy is mathematical. It's not just a mere analogy. The equations that are describing the propagation of sound waves over a flow are the same equation that describe the propagation of matter over the space-time of the black hole if the flow has a region goes from subsonic to supersonic. Okay? So imagine a flow like the drain bathtub where the flow is flowing at less than the speed of sound, at some point become equal to the speed of sound, and then faster than the speed of sound. That would not only be analogous to a black hole, it really would have for matter the same equation. So when there is such a strict mathematical analogy, you can use it. And people have been looking for Hawking radiation in superfluids, where this analogy is very strict. And not too long ago, a couple of years ago, there has been a first evidence of measurement of the analog of Hawking radiation in a form of superfluid that
for physicists is called Bose-Einstein condensate. Okay? So, I want to give you a kind of homework. You can do your black hole at home. How? Using this analogy. In this case, what we can use is an analogy which is related to surface waves. You know that if you have a shallow basin and you look at the ripples that are moving on the surface of the water under the influence of gravity that is pulling them down, the velocity goes basically like the square root of the height of the flow. So imagine you have your sink in the kitchen, like this. And now you put the plate like this. What is going to happen? You can do an hydraulic jump. From your tap, the water flows down. You can try to make it as less turbulent as possible. And then, what is going to happen? Here is very shallow, the flow. So, the speed is very low. So, it's very easy to reproduce the time reversal, the contrary of a black hole. What is called a white hole. Something from which nothing can enter in, instead of nothing can escape from. So, in general relativity, every solution has its time reversal. So if there is a black hole, there must be a white hole. In nature, we don't think that they are reliable. It's not so clear, but that would be cool and a matter of science fiction as well. But in spite of this, you can do it in your tap. There is an experiment, and you will see this.
Make your own white hole at home. Experiment number 1.
There is no number 2 because... So you see this ring, this is the ring where the flow escaping from the tap is reaching the speed of the surface wave. So I try to push waves inside and they're bouncing back. So this is, of course, turbulence, it's not perfectly analogous, but it is making at home a white hole. And you can do it at your house and you can show that you're able to manipulate black holes in your, white holes in your kitchen sink. So, moving on, now we are living really the realm of unknown things. Who can guess what is this movie? You need to be old enough. The Black Hole by Walt Disney, 1979. So let's see how they describe the interior of a black hole. They are falling into the black hole. I don't know, psychedelic eye. Now, if you remember, there is a bad guy, the doctor. The doctor is floating in the black hole without any spacesuit. There is wind. Lots of wind in the black hole. Very windy. Bring with you a scarf. He's not amused, as you can see. He's not. No, definitely not amused. Now you see the alien robot. Now we don't know what is happening. I don't want to comment. And he finds himself into the robot. And then the robot lies on a rock in the middle of the flames. I need it. At this point, I need it. Just joking. But, okay. You know what I mean. I'm saying. So, let's try to see. First of all, it's really complicated to say what happens if you fall into a black hole. The first things I want to say is that you may not even be able to fall into a black hole, at least not alive. But the good news is you can fall into a black hole and stay alive. Just pick up a very big one, a supermassive black hole. Why? Because basically the black hole is exerting on your head and your feet a different force. It's the tidal force. We are used to tides created by the moon, right? The black hole is a bit more, say, energetic than the moon, and the tides are a bit more extreme. So if you fall into a black hole, and the black hole is the size of a stellar mass black hole, you're gonna die like a spaghetti. Okay, for me, being Italian, it can even be a nice death. But I think that apart from the Italian case, I mean, it's definitely not a nice way to die. However, if you pick up a very large black hole, then a supermassive one, 10 to the 6 solar masses, then you have a chance to fall into the black hole and not die. It's easy to understand why. Where the things are getting extreme, at the center of the black hole, where the so-called singularity is, right? And then we will comment about the singularity. If the black hole is very large, the event horizon, the border of the black hole, is very far from the singularity. If it is very low mass, it's very close to the singularity. So if it is very massive, you cross the horizon very far from the singularity and nothing extreme happens, right? However, it's still, I mean, sooner you die, at the end you die. Because, I mean, the tidal forces sooner or later will get rid of you, okay? There is much more to say, but let's stop for... What I'm going to show now is a simplified movie where I show you the simplest black hole, the one that has just a mass but doesn't rotate and doesn't have a charge. And I'm assuming that this black hole doesn't have matter falling in, because if there would be matter falling in, inside there would be a mess. You will have stuff, you fall into the black hole, you will have stuff racing behind you and compressing, becoming a kind of pancake, a layer, a shell of matter falling behind you, and becoming a kind of singularity itself. And then you will have the matter that has fallen before of you, reverberating part of it from close to the singularity and coming back at you. So you will be taken between these two pancakes and you die. But here we don't die this way, we just die by the standard singularity at the center of the black. So let's see what happens. First of all, the green area is, well, let me say the only salient thing is this. This red circle is the horizon, here. So when you get here, you cross the horizon. When you are inside, you're inside a black hole, and then there is the yellow, is the last unstable circular orbit, but these are technical terms, they are not relevant. You will see that the sky, once you fall into the black hole, doesn't become dark, because of course light can keep falling into the black hole. It doesn't obscure your vision of the rest of the universe, but it will close on you, because gravity is pulling so much that basically light is focused. And you will see the sky becoming a smaller and smaller circle. It's not so well clear explained or easy to see in this animation, because it's also very fast. And then you arrive at the singularity, and then the movie ends. But I didn't want to say you died. So first of all, what we are seeing here, you see the light that is around the black hole is deformed, is moving around. You see even the stars behind the black hole, basically for what we said before. Now this grid is just artificial, it's there to show you where the horizon is. And now you see when you are getting closer and closer to the horizon, you will see that at some point we touch the horizon, we enter the black hole. And look at the sky above, you will have an effect where it starts to be... Now we have touched the sky, and now you see things are closing up rapidly, and boom. End of the story. Now, what we have encountered is the so-called singularity. And singularity, I want to make it clear, is a fancy name for basically something where physicists go, okay, I don't know. Because basically we don't know what is going on there. What we know is that space-time arrived at a point where basically the equation written down by Einstein, the equation we saw at the start, do not predict anything. It's not that we have a prediction and there is some, like everything goes to infinity. No, there is no space-time as determined by the Einstein equation. So we don't know the answer there. We can know, there could be another universe, the entrance to another universe. There can be the presence of a sort of traversable wormhole. We don't know. At the end, if someone wants that, we can have a discussion about, for example, interstellar take or what replaces singularity. Well, then we move to stranger things, definitely, because the black hole, as I told you, were the most conservative part of this talk. So, of course, stranger things, I think it's more fantasy, still fun, but so let's see. What I want to discuss is time travel, which is, of course, is another classic of science fiction. Now, I must be very clear. Physicists do not like time travel in general. Okay? And generally, we don't like time travel because once you try to make sense of it, it's very difficult. Now, first of all, let's be clear. Time travel is problematic only if you travel back in time. Actually, Einstein already tells us that we can travel forward in time. So, you know, it's very simple. Pick up a black hole. So, take your spaceship, go close to the black hole. As the clock on Earth is slowed down with respect to the clock far away because of the gravitational field of the Earth, what is going to happen if the clock is lying very close to the horizon of a black hole, the most dense object you can conceive? It will almost stop. So, few minutes of your life close to a black hole, an hour close to a black hole, will be years on Earth. And this is basically the crucial point in the plot of the movie Interstellar, right? When they are on a planet close to Gargantua, the supermassive black hole, they stay there for 1 hour, they come back, 7 years passed for the spaceship which was far away. But that is not a problem, there is no paradox associated to this. But let's see what happens if you travel back in time. Well, there are two forms of paradox. The first one is the well-known grandfather paradox. So you travel back in time, and without even wanting, you meet your grandfather, and you just push him in the wrong moment, and he doesn't jump on the bus where he was supposed to meet your grandmother. So at that point, how you can be there doing any action because you were not supposed to be born anymore. So the grandfather paradox is really a paradox of consistency. This is why physicists don't like it. And you can do physics in a universe where these kind of things are possible. The bootstrap paradox is something similar. Imagine that you are really passionate about Beethoven, and you travel back in time and you want to meet Beethoven. Now, when you meet Beethoven, you discover that Beethoven is very depressed and doesn't want to write his, the 9th Symphony. And you're like, what? And then you don't know what to do. Then you say, okay, I can do something. I can pass to Beethoven the 9th Symphony, because I know that I can. So you give Beethoven, and Beethoven, take that, it's some ideas of mine, do whatever you want. And Beethoven, this way, writes the 9th Symphony. Well, when you then are back and you're listening to the 9th of Beethoven, basically, you have basically at the right moment to go back again in time to close the circle. In a sense, who wrote the 9th of Beethoven? Because in your history, you gave it to Beethoven. But you gave it, but you had it from Beethoven. So there is something really wrong. And then if you decide to not come back where the 9th Symphony was coming from, then it becomes the grandfather paradox. So this bootstrap paradox is even more... Well, of course, physicists are very inventive people, and they try to find a way out of these paradoxes. Oh, okay, sorry. Yes. So before we go back to paradoxes, let's say how you can make a time machine before worrying about the paradoxes. Well, the time machine, the problem is that they are really very easy to make in general relativity, amazingly easy to make. So basically there are two ways. One is to have a rotating solution. You take some matter and you make it rotate enough fast, you will bend the structure of space-time so that it's possible to travel back in time. So rotating solutions are of different kinds. Here you can have cylinders of matter, you can have a rotating universe like the one invented by Kurt Gödel as a birthday gift to Einstein, to show that general relativity not only hadn't a preferred time, but basically had solutions where time was meaningless because you could travel back in time. And then there are even phenomena of this sort in the interior of rotating black hole, but they are shielded by the event horizon, so people generally don't worry about it. And then there is another way, and the way is called shortcuts. So if you have a way to cheat the fact that nothing can travel faster than the light, then you are in trouble and you can very easily create a time machine. And the two most famous shortcuts are wormholes and warp drives. So let's see what they are, because while these solutions are very abstract or they're part of the geometry of a black hole, but in the interior where nobody can access, these other solutions, wormholes and warp drive, they require exotic matter, a matter which has negative energy density. But you see, the problem is that we are able to create small quantities of this matter. So it's not that there is a theorem telling you this matter is forbidden in nature. So let's see what they are. So here is a movie, is an excerpt from Interstellar, the movie, where they reach close to the wormhole. So first of all, is it clear why the wormhole appears as a sphere? Because normally we depict the wormhole as something that is puncturing a sheet like this, no? And then you puncture and you have two dimensions, and you have a circle. But now you have to add the dimension because space-time is, the space is three-dimensional. So a circle becomes a sphere. So you see a sphere. And this is really a true rendering of what a black hole, a wormhole would look like. In fact, there is a scientific paper out of this movie regarding wormholes. So wormholes are these shortcuts, and it might look that you need an extra dimension, but you may think that it's physical, but you don't need it to write down the solution of general relativity that describes a wormhole. So you don't need to think of a fifth dimension. So they were, and there is a solution which is a traversable wormhole, which was proposed by Kip Thorne, the same guy with the Nobel Prize of this year, for his friend Carl Sagan, that was writing a book called Contact, which was made in a very famous sci-fi movie as well. So just to give you an idea, you need exotic matter. For a 1 meter traversable wormhole, you need just a Jupiter of exotic matter. So, okay, I mean, it's a Jupiter, but still it's an engineering problem. It's not this is the problem, right? So, warp drives. Okay, these warp drives is interesting. Warp drives were invented by sci-fi before they were found in okay, it's obvious which this is. And you know, what is actually a warp drive in general relativity? It's a way to cheat the limit on the speed of light. So what do you do? I mean, the speed of light tells you that locally I cannot send a signal faster than light, right? The limit. But imagine I take space-time and I do a bubble of flat space-time, and I made in such a way that space-time expands behind and contracts in the front of this bubble. Inside the bubble, everything works like in special relativity. Basically, you send signal at the speed of light. There is no strange things going on. But you see, the laws of Einstein do not pose any upper bound on how fast this bubble can move in space-time. That is a part of space-time with respect to the rest of space-time moving, and there is no upper bound to that speed. So if I now have built a kind of rail, you know, a track from here to Alpha Centauri, where I have some kind of devices that are changing the vacuum, they are making the exotic matter in the right moment in such a way that this is pushed like in a magnetic monorail. And then you can go, after the first time, you can go as fast as you like. Now, you may say, okay, but both of these methods are not time machine, are way to cheat the limit on the speed of light. Why they are related to time machine? And the time machine is because once you have these kind of shortcuts, you can turn them in time machine very easily. One way to do that with wormholes is, for example, to put two wormholes. So you go from here, inside a wormhole, and you can always get there and get another wormhole to come back before you started. Or if you like, take a single wormhole. These are 2 points in space and this is time. I can always make this. At that point, I can travel backward in time. And this spells trouble before what I told you. So
the same things can happen with a warp drive. You do one way and you travel that. Given that you can travel at arbitrary speed, you can always close the circle in such a way to come back before you start. No good. So, of course, what the physicists thought about way out. One way is to say, okay, if general relativity say that this stuff is permitted, then time travel is permitted. It's just a matter of building this wormhole sort of warp drive. And then you have to accept that, for example, the grandfather paradox, one way to solve it is then, if you kill your grandfather, even accidentally, you must be really very clumsy, but if you do that, you branch in another universe. There is a branching every time you change the past. And there is a universe where you didn't arrive and you didn't influence the history and you were born. And another universe where you were never born. Okay? So you have to do physics basically on a completely new mathematical basis, which is something that people prefer to not do. And I'm just citing here a movie where this kind of branching of histories is used. Then there is the Novikov conjecture. This is like a real socialist conjecture, in the sense that if you allow time travel and you can change the past, in reality you can't. So Novikov would tell you, try to go back. Try to, for example, kill your grandfather. Not only you will not succeed, but your action will be exactly the action that were needed for history to go the way it went. So, for example, you will try to kill your grandfather, but then you miss it, and you kill the guy that instead was going to marry your grandmother. And your grandmother then was consoled by your grandfather, and they got together, and exactly the story it went. So there was the agent, you play as like the mysterious agent that make them meet, exactly as history was told. So you cannot change the past. So people has tried to create pool table models with three balls, which are basically periodic solution. But it's very difficult if you think the complexity of reality that this may work. Then, of course, there is the Hawking chronology conjecture, which is very simple. They cut the things short. The laws of physics will forbid any time machine. If you try to create a time machine, it will explode in your head. Okay, the nice part about this is that it seems to be true. It seems to be true in the sense that if you try to create a time machine, you can show that there is an accumulation of energy close to the moment in which the time machine is going to appear. What is happening is that at the moment in which, for the first time, you can close the temporal loop and come back exactly at the moment you started, there is as well the quantum energy of the vacuum that reacts to this and is self-amplified. It's like in a kind of Larsen effect, you see? So it's like when you put a microphone very close to a speaker. Then you have this self-amplification going on in the energy, due to the energy of the vacuum that in quantum mechanics is something dynamical. It's not really empty. And then basically you get to something parasitic that is going to make your time machine explode. However, and this is why I say they almost, there is a theorem that tells you that the current physical law that we're able to apply break down close to the formation of a time machine. So you cannot carry on the calculation until the end. So you cannot achieve a conclusion. And it seems that you need a quantum gravity, the theory that puts together gravity and quantum mechanics. Damn it. So this is what... However, it's not so disparate, the story, because you see, some years ago we did with a graduate student friend of mine, a colleague of mine and a graduate student of mine. By the way, this guy had never seen Star Trek or Star Wars, so you can imagine what happened to him when he started a PhD thesis in this subject. His fellow students they obliged him to see the old Star Trek movies in one night, one weekend of Star Wars, terrible things. So I'm going to close very soon. So I just want to say, we did a calculation. So we did, what happens if you try from nothing to generate a warp drive? From flat state, you generate a warp drive and you dynamically create it. Is it going to be stable or not? So it's not asking if a time machine is stable. It's basically asking, is the tool with which you would build a time machine going to be realizable in nature? And so we did a similar calculation to the one that Hawking did for predicting the evaporation of black holes. So we did quantize the matter, and we considered the space-time where there was this warp drive. The story is very simple to tell a posteriori. And a posteriori works this way. Imagine you are in the bubble, and you are moving faster than the speed of light. From behind you, from the rear wall of the bubble, nothing can get in. Why? Because signal cannot travel faster than light. So for you, it's a dark wall behind. In the front of the wall of the bubble, nothing can escape from inside the bubble because the wall is moving away faster than the speed of light. So this is the analog of a black hole horizon, and this is the white hole I showed you before. You can do in the city. Okay. So what it was happening? That quantum mechanics predicted radiation, like Hawking radiation, coming from here, moving this way, accumulating on this side because it couldn't escape, and exponentially growing and making the warp drive explode. So the moral what it is that not only the radiation was also very high. So you see, you cannot cook the dragon omelette if you don't have the dragon egg. So it looks like quantum mechanics, when it's married with gravity, is forbidding even the tools with which you will do the time machine. So this was a very interesting lesson for us. But I don't want to scare, to be too depressive about the time travel. About time travel, yes. About traveling very fast is another matter. So let's conclude. What next? Well, what we have seen is that extremely warm space-time and time travel region most probably are going to be forbidden. Understanding how, however, is very important. I like very much a sentence which is in one of my favorite songwriters, which is Leonard Cohen, which is that there is a crack in everything, and that's how the light gets in. And you see, for us, you may wonder why people doing physics is taking so much time on stuff that, all in all, is interesting primarily for science fiction at the moment. We cannot, at the moment, build a warp drive. It's not just the idea that maybe in the future we can build a warp drive. The problem is that you are pushing the theory to the limit. And it's only pushing the theory to the limit where it really, you can see where the crack is and where you can go beyond. A drama in physics is when you have a theory that works too well. For example, the standard model in this moment. It's very difficult to go beyond if you don't have a glimpse of new physics beyond. And general relativity is showing us that there are parts of general relativity that demand more predictivity, more information. So I'm just saying that one last thing. What we found is that superluminal warp drive are forbidden. But if you go even 99.99999% at the speed of light, so you are subluminal, then nothing of the stability that we saw appears. It's just a discontinuous thing. It's not unstable. So at that point, if you want to go with a warp drive and travel at 99% of the speed of light, then it's doable. So bring the engineers. So in conclusion, I just want to say, these are very interesting things to discuss about, and I will be happy if you like to discuss more about the ideas about the singularity and so on. But I think it's time to close here and to thank you again for the patience. This is how the geometry of a warp drive will distort the image of a planet which is passing in front of it. This one is allowed.
Okay, thank you very much, Stefano. We have time for a few quick questions.
I'm confused about why the drive is actually within. So what is it that's happening at the front end?
Yeah, what is happening at the front end is that the front end is moving, imagine the warp drive is moving faster than light, at some point. So if I send a signal from the inside the bubble, it's moved at the speed of light. But for him, at the front end, it's moving faster, so he will never reach it. He will have to accumulate. So it's basically the front end is really the analog of the white hole we saw in the analogy in the top. So all the signals, so the back end will generate the analog of Hawking radiation. This Hawking radiation fills the bubble with radiation at a given temperature, which is going to be very hot, by the way. And then it accumulates on the front end because it cannot escape, it cannot penetrate the front end. And then it just grows the energy there, and you find an exponential growth.
So effectively you've got a sort of like a gravitational shock wave.
Yeah, gravitational shock wave. I'm not sure I understand what you mean, because it's like a receding wall. The stuff inside the bubble cannot move faster than light. So this wall, however, in a certain sense, it can be penetrated. If it would be able to penetrate, for a moment it would have been gone faster than light, because it's moving in the outside. You would see light exiting from a surface that is advancing beyond the speed of light. So it's really accumulating there and then growing exponentially and destroying your bubble.
So what you need is the donkey and the carrot thing. You suspend a black hole in front of your spaceship to absorb the Hawking radiation.
The black hole inside the bubble in which I'm trying to travel. Well, there are many ways you can die. I can actually
Have you just been sent here from the future to put us on trying to invent time travel so that we don't make a mess of the future and past as well as the present?
So, well, what is the question? Sorry.
Well, I was saying, have you been sent to us from the future
No.
in a time machine in this way that's from inventing a time
Yeah, no, definitely. No, yes, I am coming from the future. No, definitely not. But no, I think that what I'm presenting you is a kind of mainstream opinion, in the sense that most of the physicists nowadays would align with the chronology protection conjecture. There is a lot of support from that conjecture, but that would require definitely quantum gravity to be definitively proved. But I find this interesting, the hint from the warp drive, because it's showing you that without quantum gravity, already the dragon egg is not available.
What would happen if the Starship Enterprise, travelling at warp speed, crashed into the Earth?
Okay, so warp speed, what is exactly?
Light speed. Warp 1 is light speed. Warp 1 is light speed.
Okay, warp 1 is light speed. So if something crashes on Earth at the light speed, well, I think that basically, apart from the fact that if it has a mass, it cannot, okay, so warp drive, we're talking about warp drive. We're using the warp drive technology. Well, you will make a disaster. You will basically pierce the Earth and destroy it. But why do you want to
It's like a good film, I think.
Okay. So, why thinking always the most catastrophic hypothesis? I mean, imagine you have a warp drive that goes at 99% of the speed of light. Basically, you can visit the next habitable or Earth-like planet.
But they have to slow down before they get there,
in a year. You have to slow down. That's
so you can imagine something just hitting.
It's true. You have the problem of slowing down. But if you build the warp drives, that is something that, in a certain sense, is solved with a construction.
Something might be in the way. Something could just travel in front of you. Which is pretty empty.
Yeah, maybe something is traveling toward us, you mean?
Well, yes.
I don't see any railway, anyway, between us and Alpha Centauri.
I think I took from your talk there's still a big gulf between science fiction and science. I was going to ask, is science fiction helpful to stimulate creativity?
Well, the warp drive.
Physicists,
The wormhole and the warp drive. The wormhole was created, was found the solution by Deep Thorne and Morris, just because it was inspired by, they were trying to find a way for the protagonist of Contact to travel between two guys. The warp drive was inspired by Star Trek.
Okay.
Was found by a Mexican relativist called Miguel Alcubierre. In fact, sometimes it's called Alcubierre warp drive. I just want to say that the gap is not so huge. For example, Interstellar, which was the script was written by Kip Thorne, the future the Nobel Prize of this year, together with other people. And that movie makes a lot of efforts to be as trustworthy as possible on the science. It doesn't completely succeed at it. It's still an Hollywood movie. But definitely it's not bending the rules too much.
Last one.
Okay. So, going by the idea that if you used to go back in time, you create another universe with separate events. By trying to go back to the future, would you be back to the future after that? Would you be going to the future of the new universe or back to your own? Because surely you're now stuck in.
I don't know the answer to this question. It depends on what rules you put to your branching universe. But it's definitely possible that you can imagine if you have a branching universe, then it's not obvious that once you are on the wrong branch, you can jump on a nearby one. We don't see at the moment evidence for parallel universe. Or some people say that quantum mechanics is some evidence, but that is a matter of interpretation. We will enter in a very slippery subject. But definitely, it would be possible that you would be trapped in the branch in which you were not going to be born. So to avoid any paradox, it would be even more consistent and not be able to come to the universe and meet your former self or your future self or whatever. Right. Shocked.
Well, I think so many illusions have been shattered this evening. As a mere biologist, I thought that Star Trek was absolutely gospel truth. But clearly it's not. And I mean, it's been a fascinating lecture, Stefano. I think all of us have been amused, entertained, and educated, which I think is the goal of all public lectures. And you've done it splendidly this evening. I'm a bit disappointed that you didn't go into some of the more wild ideas of Douglas Adams around the Big Bang Burger Bar and the restaurant.
Well, there was no time, as you've seen.
But maybe we bring you back for that another day.
Yes.
But anyway, I'd just like to thank you again for such a wonderful talk, and I ask you to join me in thanking Stefano.